Okay, this is some more details on Lewis structures that you'll need before you start practicing. So, we want to talk first about multiple covalent bonds. So far we've talked about things that are bonded to one other thing. And we've done some Lewis structures with these. Let me replace that. We've done some Gooch math, so you know how to find the number of valence electrons, the number of octet electrons, how many are shared, how many bonds there are, all that. Well, now we're going to talk about some cases where there seem to be more bonds than you could possibly stick into something. Let's look at a case in point. Let's take C2H4. This is also called ethylene. It's a gas that's given off, pardon the messy writing, a gas that's given off by fruits and vegetables. It's actually flammable. It's got a mild odor. But what we want to do is draw a Lewis structure for it. So in order to do that, we're going to start with our Gooch math, and we're going to start out by figuring how many valence electrons everyone brings to the table, step 1. So each carbon, if you remember, carbon starts off looking something like that, is bringing 4, and we have 2 of them. Each hydrogen is bringing 1, and we have 4 of them. So we have a total of 12 valence electrons to begin with. Now, if everybody was satisfied with their lot in life, if everybody had a full octet or their version of an octet, each of those carbons would have 8. There are 2 of them. Each of those hydrogens dream of having 2. Though, remember, hydrogen doesn't dream. So that's 16 and 8. That would be 24 electrons if everyone was fully satisfied. If we subtract the valence electrons from the octet, 24 minus 12, we end up with 12 shared electrons. And since each bond requires 2 electrons, when we divide that by 2, we show that this is going to have 6 bonds. Let me shrink this. So I have carbon, 6 bonds. Well, I know that hydrogen can only bond in one spot. So I know that hydrogen has to be out on the edges somewhere. Oops. And, darn it. So we'll hook the carbon to the hydrogen with single bonds. Like I said, carbon can only bond one time. Well, we know that this carbon can also accept 2 hydrogens. Now we've got 1, 2, 3, 4 bonds. We have 2 left. We only have one option. There must be 2 bonds between the carbons. And in fact, that's the case. Ethylene has a double bond right in the middle. Carbon is famous for bonding to itself 1, 2, and even up to 3 times. So that does happen. Now, let's look at how many unshared pairs of electrons there are in this. This is the 6th step of the Gooch math. So if we know that they are sharing 12, we start off with our valence electrons, 12, and our shared electrons, 12. There are no unshared pairs here. Every single electron is being shared. Now we're going to do the typical check to see if everybody's happy from an octet perspective. We'll start off with this hydrogen. It feels like it has 2 electrons. It's satisfied. This hydrogen, 2 electrons, satisfied. This carbon feels like it has 2, 4, 6, 8, satisfied. This carbon feels like it has 2, 4, 6, 8, satisfied. This hydrogen, 2, satisfied. This hydrogen, 2, satisfied. Whoops. Be careful on those little red traces. We don't want to make that look like a double bond. They're still single bonds. Okay, so, and if you remember from the story of the propane versus the MAP gas, multiple bonds double bonds tend to be shorter than single bonds. Triple bonds tend to be shorter than double bonds. And the shorter the bond, the more energy is contained in the bond, or the more energy it takes to break that bond. Okay, let's practice one more with multiple bonds. O3 is also known as ozone. It's a critical component of our atmosphere. Up in the high atmosphere, it protects us from the sun's UV radiation. However, down here at the ground, where ozone is often a byproduct of electrical motors and other industrial processes, ozone's a pollutant and a major contributor to smog. But, aside from all that, let's do the Lewis structure for ozone. So, this is pretty easy, right? We want to figure out how many valence electrons everybody brings to the table. Well, oxygen brings 6. There are 3 oxygens. That's 18 valence electrons. There's nothing else to contend with. What about octet electrons? If everybody was satisfied, how many electrons would we have? Well, oxygen would like to have 8. There are 3 oxygens, so that's 24 octet electrons. If we subtract those, 24 minus 18, we get 6 shared electrons. And if we divide that number by 2, we see that there are 3 bonds. Let's go ahead and look at the number of unshared electrons, because that's sort of telling here. So they came in with 18 valence electrons, and they're sharing 6 valence electrons. So there are 12 unshared electrons. Okay, let's take all this information and attempt to draw the Lewis structure for ozone. Well, we know we have 3 oxygens, like this, and a handy thing to do is to start off by just hooking them together with single bonds. That doesn't take care of all the bonds that we have, though. We have 3 bonds. So we know that there must be a double bond in here somewhere. So we'll go ahead and put a double bond here. We now have all the bonds accounted for. Fantastic. Let's get those unshared electrons in. So we have 12 unshared electrons, or 6 unshared pairs. So let's look at each of these molecules and decide how many other pairs of electrons they can take, looking at this from a perspective of whether or not they're satisfied with their octet. So we'll start off here. This oxygen feels like it has 2, 4 electrons. So it would like to have 8. So 2 of those unshared pairs will go, let me make that a little bit neater. 2 of those unshared pairs will go on this oxygen. The central oxygen has got 2, 4, 6 electrons, or so it feels. So it would like to have 8, so one of those unshared pairs will go there. The oxygen on the far end only feels like it's got 2 electrons. So it's going to have 3 unshared pairs. Now, let's check to see if each of these atoms is satisfied based on octet. 2, 4, 2, 4, 6, 8. That one's happy. 2, 4, 6, 8. That one's happy. 2, 4, 6, 8. That one's happy. All of them are happy. They all have a full octet. All of our bonds are accounted for. All of our unshared electrons are accounted for. Well, this is probably a good time to bring up the next concept. That would be resonance. So as a matter of fact, ozone is one that's really commonly used to demonstrate resonance. Here's the question. How do you know that the double bond's over here? How do you know that the single bond's over there? The answer is that we don't know. So what we have to do is represent that bond in both places. We only have to do this if there's a double bond that could exist, or a triple bond, that could exist in more than one location. If it only can exist in one place, or if there are no double or triple bonds, then there's no resonance. It used to be thought, well, let me show you first how you show resonance. So for this ozone molecule, we would show it with the double bond here. Let me put in my... So we show it that way. We then put a double-headed arrow, and we show it with the double bond in the other location. And we also have to, of course, add the unshared pairs in the correct location. So what this indicates is that this molecule can exist either in this state or in this state. The double-headed arrow is really important, as is showing that double bond in every location where it could exist. It used to be thought, interestingly enough, that molecules like this went back and forth between the two states and that double bond would move. What is now better understood with more modern analysis techniques is that they actually exist in this sort of hybrid state between the two of them. So it's almost as if there's 1.5 bonds in each location. But we can't show that, so we stick with resonance. Okay. The last thing I want to talk about is a concept that kind of jumps order with your notes, but I want to address it here and then we'll hit it again later. That concept is polyatomic ions. So in some cases, you can have two atoms that are bound covalently, that is, they're sharing electrons. We'll use the example of oxygen and hydrogen. They can be bound together. And then gain or lose an electron as a group. This is called a polyatomic ion. It's an ion that's made up of more than one atom. And we represent ions when we're drawing them, when we're drawing polyatomic ions. We represent them in much the same way we do any other compound. So let's talk about OH1 minus. And let's do the Gooch math for this. This is, by the way, the hydroxide ion. It becomes very important later. We'll talk a lot about it. So when we're doing the Gooch math for an ion, the only big difference is that we have to account for the fact that there's either a few extra or a few fewer electrons than we would otherwise think about. So first we figure out how many valence electrons there are. Oxygen, of course, came in with 6. There's 1 oxygen. Hydrogen came in with 1, and there's 1 hydrogen. So that would give us 7 valence electrons. But wait, don't answer yet. This has a -1 charge, which means somewhere it has picked up an extra electron from the environment. So that makes us add 1 valence electron. So we have 8 valence electrons. Okay. Well, now how many octet electrons would we have if everyone was fully satisfied? Oxygen wants 8, hydrogen wants 2. That gives us a total of 10. So they have 8 valence electrons, but they would like to have 10. So 10 minus 8 means they're going to be sharing 2 electrons, which means 1 bond. Now, it's very important here to calculate the number of unshared pairs, because that's typically where these extra electrons get either picked up or given up. So the number of unshared electrons, if they have 8 and they're only sharing 2, there are 6 unshared or 3 unshared pairs. Now, let's go ahead and hook these things together. So we know we only have 1 bond, and there's really only one way to bond these two things, right down the middle. But how many unshared pairs do we have? 6. Well, hydrogen can't take any, or we have 6 unshared electrons, 3 unshared pairs. Hydrogen can't take any unshared electrons, so oxygen is going to have all of them. Now, how many electrons, this is where knowledge of what they looked like before they bonded is helpful. If you remember, oxygen came in with those 6 valence electrons, most often pictured like this, and hydrogen came in with just 1 valence electron. If we're thinking about pairing these things up, it looks pretty obvious if we kind of do the old physical science method of moving these things around. Okay, well that sort of fits into the slot like a puzzle piece, but then we're missing an electron here. So this entire compound pulls an extra electron from the environment and forms then a polyatomic ion. So in fact, you get that sort of extra electron there. Now, when we're showing a polyatomic ion, we draw the Lewis structure, but then we have to enclose it in a bracket because we always enclose ions in brackets when shown in a Lewis structure. And this one would show the charge out here on the outside, so we would say that. And we would if you don't show the bracket and the charge, it is wrong. Okay, with that, you know how to show double and triple bonds. You know how to show ions. You've got some practice problems linked on the Google Classroom page. So go get the practice. You can do it on paper, longhand. You can do it in Doceri. I don't care. Key should be up by the end of the day on Wednesday, and we'll grade them and go over them on Thursday. Have a good night, or have a good day.